first speaker this morning is Michael McIntyre from just up the road. Beyond Lighthill, picture of Lighthill, 3 ways to stay close to balance.
Thank you very much, Mike. I understand we're running to the time as shown on that clock rather than the Greenwich Mean Time. Is that correct? That clock's about 2 minutes slow. Thank the organisers for inviting me. It's a privilege and honour to be at a meeting so full of the great people in the field and all kinds of interdisciplinary fringes, which I always love, the cross-disciplinary communication, and I try. My main theme is balance and imbalance, but I also want to spend a little time on some really hot off the press stuff. In fact, it isn't off the press, it's in the press. It's going toward the press, it's progress toward a generalized Paparella-Young theorem for horizontal convection. I regard this as a very basic piece of theoretical fluid dynamics relevant to understanding the oceans and therefore indirectly their impact on climate. But the main part of the talk will be on balance and imbalance, as I originally promised, of whom 2 of the great names are James Lighthill and the late, sadly deceased Rupert Ford, who by now would have been a top international star, I'm quite sure, if he hadn't died prematurely in 2001 by being careless over his diabetic condition, which was a terrible shame. As Dr. Sugimoto already reminded us, the distinction between balance and imbalance is inherently fuzzy, and I'll come back to that after talking about the Paparella-Young theorem. You might say Paparella-Young-Sandstrom theorem. It's about the problem called horizontal convection, where you do a thought experiment in which the ocean is driven only by buoyancy forcing at the top, and the question is, can the convective plumes and gravity currents that result from that, deep water formation and so on, can they do enough stirring to close the circulation and produce an ocean anything remotely like the ocean we observe, in which you have stable stratification almost everywhere, including the abyss. It's now clear, some fraction of a cycle per hour, the buoyancy frequency, wouldn't it be, Peter? So it is stably stratified, and so, as Walter Monk pointed out eons ago, you've got to have some kind of diapicnal mixing to close the circulation and permit. But what?
It's only
90. Walter is 90. What, today? I should have dedicated it to Walter as well. But funnily enough, I got an email from Walter about concerns about climate change. He thought I knew more about that than I do, but never mind. Somebody's suggested putting loads of small nuclear reactors everywhere, so you've got a distributed energy system, but they don't say what they're going to do with the waste. And let me get off that. Walter's a wonderful guy. I'm sure he has some interesting thoughts on all this. Okay, now about this problem. By the way, I don't think the answer to that is really obvious. There's been a controversy between Monk, Wunsch, and others, including now myself as well as Bill Young, and mainly the Canberra school, I think, Stuart Turner, Ross Griffiths, Graham Hughes and company, about whether these, and I can't quite get hold of what they're saying because they don't ever quite say it, but what I think they think, and someone who knows more about this could correct me if I'm wrong, I think they think that the convective plumes can do enough stirring to close the circulation, and you absolutely don't need any mechanical stirring from wind and tides or fish or whatever. It's been seriously suggested the fish may contribute significantly. I don't know whether anyone's quantified that because...
Yes.
What?
Yes.
Is that clear, Jim?
No.
It isn't clear.
It has been quantified.
It has been quantified. Well, Bill Dewar, but has he really done it convincingly?
No.
No, I thought so.
That question.
This question?
Yes.
What does Bill say about that?
That I don't know. But that also has not been clearly answered, as you're telling me.
All right. Well, it's controversial. I would argue that actually this result I call the Paparelli-Young theorem suitably generalized will actually constrain. Jim, what are you saying?
Don't interrupt the audience.
Well, all I can do is give what I think my current understanding is. Okay, it's controversial. I don't think the answer to that question is obvious. Peter Rines tells me the whole thing is obvious, but I don't think, Peter, would you say the answer to that is obvious? Really, until you do some theoretical work?
Yes.
You think it's obvious? but I think you were saying you don't need the Paparelli-Young theorem to know that.
I don't think this lecture's going the right direction, Michael.
Come on, be honest.
I think I'd rather hear what you have to say.
Okay, the theorem I think does bear on that question, and let me just stay with that position for now. Now, part of the trouble with the whole controversy is this word drive, and the older I get, the more I see that this is one of the most ambiguous and misused words. You hear again and again scientists arguing, oh, it's all driven by this, or it's all driven by that, and quite often it's forgotten that the word has at least 3 distinct meanings, which you have to be explicit about. This is the explicitness principle. You must be at least twice as explicit as you feel necessary if anyone is to make any sense of anything. Let me just give you a quick illustration of this. Well, Sir James Jeans had the same problem in astrophysics about a century ago. One of the meanings of something is that the driver is on the right-hand side. Now, of course, once you expose that and make it conscious, it's obviously silly. So if you have an equation A equals B, people often unconsciously assume that B is causal. B drives A. B is a causal influence on A. But of course, and the trouble is there's an unconscious confusion with a Fortran statement in which it really is true that B causes A. Yes, it looks the same, but it doesn't mean the same. And Jean's example was where A is the room temperature and B is the thermometer reading. So the thermometer keeps the room hot, said Jeans, just to expose how ridiculous this is. But you might think I'm being really silly, but half my career has been spent in trying to understand stratospheric dynamics on the Earth, and there's a huge literature in which exactly that fallacy keeps on being made. It takes the form, the Breuer-Dobson circulation is driven by solar heating, and the reason people say that, I think, is that you've got a heating term on the right and a circulation term on the left. Well, it's completely absurd. You have to remember that the heating is a relaxational process and so on and so forth. That's rather old and well understood now. Other meanings, the other 2 meanings of the word drive. Well, when you drive an automobile, it means you control it, doesn't it? But people often mean that there's an energy source, which is a different thing. Now, here's an audio amplifier with a minute signal going into the input and a huge signal coming out of the output. And the 2 senses of the drive are that the automobile sense says that you're controlling the input and getting the big output, and that's what drives it or controls it. But the energetics person says, oh, no, it's the battery that drives it, you fool. The energy input is so negligible here that it can't possibly be important, they say. And I assure you that that kind of thinking is part of the problem with the controversy to which I refer. Now, of course, it raises the question, the sort of questions I'm really interested in, can they be answered by examining energy budgets? And of course, no, they can't. By the way, energy budgets are very complicated. Energy budgets are interesting. I'm all in favor of energy budgets, so long as one doesn't think that they're the answer to everything, that they're the only way to explain things. And in the case of my audio amplifier, for instance, the way the energy gets from the power source into the amplifier is through the pointing vector, which has a field that looks very crudely like this, and it's all outside the wires, you see. It goes through space. So if you just think of nothing but that, it's very mysterious why breaking the wire would stop the amplifier working. So there it is. Now, a lot of the time, as I hinted before, is if you say, it's a good idea to say what your thought experiment is. Is it to vary the input or is it to cut the power? It helps to make that explicit. Now, I think and Peter and Jim might disagree with me, that a key thought experiment about the ocean is to hold the temperature and salinity distributions constant, or in some distribution, cold at the pole, warm at the equator, and so on and so forth, at the top surface, and stop the mechanical stirring, kill all the fish, and turn off the winds and tides. By the way, we have some idea of the magnitude of that. It's something like one electric toothbrush per cube 100 meter on the side. And so it's really, it could be that fish are doing something. I mean, it's not implausible. It's a rather small, but it's nevertheless, well, I'll come to that. Okay, here's the thought experiment. We prescribe buoyancy stuff up here and do nothing else. And this is a sort of semi-realistic ocean. The real ocean has even more complicated topography. Now, there was a landmark paper by Monk and Wunsch following on Walter Monk's original Abyssal Recipes paper, to which I briefly alluded. They argue heuristically that with no mechanical stirring, the convective plumes wouldn't be enough to do enough stirring, not nearly as much as the fish and the tides and the winds, and then the ocean would become unstratified at the maximal density wherever the coldest, the most dense, potentially dense surface water is. And I think the Paparella-Young theorem is important because it lends some rigorous support to that heuristic argument by telling you that the plumes really can't do enough stirring. If, in fact, an associated numerical estimate is they're 3 decimal orders of magnitude too weak to do the associated stirring. But the trouble is, the original Paparella and Young paper, which was published in Journal of Fluid Mechanics in 2002, is for a very idealized case only. Here's what they proved. This is a proof, by the way. There's no heuristic about it whatever. And in a purely thermal version of this thought experiment, with a linear equation of state, and all the oceanographers know that's not a good approximation of the real ocean, in a rectangular box, a much simpler geometry than that, then the global epsilon, that's to say the domain integrated turbulent dissipation rate, must go to 0 like the thermal diffusivity in a limit where you let all the diffusivities go to 0 with constant Prandtl number. Okay, so there's a perfectly definite limiting statement, and it doesn't actually say that there's no turbulence. I have a quarrel with Bill Young about this. I think I've actually persuaded him. He called this the anti-turbulence theorem, which I think actually contributed to some confusion. It does not disprove that there's turbulence in the sense of having a Kolmogorov cascade and a Kolmogorov scale. In this limited, this bound is only enough to tell you that the Kolmogorov scale could be of order the square root of the diffusivity. Yeah, so it can still be small. So you could still have turbulence in a sort of weak sense, but the real point is that the epsilon that you bound in this way is 3 decimal orders magnitude too weak to do enough stirring to give you the observed stratification and the observed bottom water formation rates of tens of Sverdrup or whatever it is. How well is that number known?
I couldn't say anything like that.
Well, let's say twiddles tens of Sverdrup, shall we? Is that fair? Recently, a beautiful lab experiment was published by Whitehead and Wang, which we only noticed rather late in the game, in which they kind of do a lab verification of this idea, which Peter says is obvious. Actually, well, never mind that. Some people think it's obvious, and I do actually, but others don't. And the thing being that convective plumes are rather quiet things, really. Okay, you take a tank, you hold a salt distribution at the top with an ingenious arrangement. So it is a version of the same thought experiment in which the only molecular diffusivity is salt diffusivity, which is low enough even in the lab. This tank is this sort of depth and about that wide, I think, a meter and a bit. And you either stir it or you don't stir it. When you stir it, you get density profile like that, and when you don't, you get it like that. So it's rather nicely confirming that Monk and Wunsch were on target. There was a predecessor experiment by Stuart Turner, although he was addressing slightly different issues in that paper. So the challenge anyway is to generalize the Paparella-Young theorem to realistic ocean models. And as I I've said that already, what the idealization they made was. Now, what we're doing, and I think we are 99% within a hard result. I would say 100 if I'd been able to check one or two rather complicated calculations sufficiently, but I'm only going to say 99. But we believe we can prove the following, that if we assume the Overbeck-Boussinesq equation is a good fluid dynamical framework, meaning Boussinesq in its most basic sense of having an infinite sound speed and an inertial density constant. Try to generalize the theorem to a realistic equation of state. This is an intermediate step. This is the equation of state in Jeff Vallis's book, in which you have two nonlinearities, a thermobaric effect in which pressure and temperature expansion interact, and a nonlinear temperature expansion. Both of those kill the original Paparel and Young theory, and it is not trivial to generalize it even to this level, but we've done that. So we have made definite progress. So this says that if you think the equation, that Boussinesq is a good ocean modeling framework, and you have this sort of equation of state, which is not too bad actually. I mean, the other nonlinearities which are neglected here, for instance, they are pretty weak actually. So on that, the convection can't do enough stirring. And if you think that was obvious before all this was done, fine, but then you have a deeper intuition about this than I, for one, could claim to have. And notice, by the way, that the Overbeck-Boussinesq framework is energetically consistent. I'm hammering this point because there's been a lot of talk in the controversy about how Boussinesq is terrible for the ocean. By the way, it is used for all the numerical ocean models, is it not? I mean, how could you possibly do an ocean model with sound waves in it? Heavens. It's accepted by all the modelers, right?
There's still some that sound up in.
Big ocean models with sound waves in?
Just treat them implicitly.
Yeah, you see, treat them separately, don't you? Well, that's the other point, you see. You can use this framework. The point is you can use it to do the fluid dynamics and the transport and the way that stuff moves around and carries heat around and so on. But you can also, and energetic consistent means what Ed Lorentz meant by that term, namely that the Boussinesq equations suitably formulated in this generalized sort of case, including this kind of equation of state, they have an energy principle. It's rather elegant actually, which can be understood as an approximation to the full energetics. Yes? This is, I think, partly work of Bill Young. It's sketched in Jeff's book, actually. And the other point is that you can use it to compute sea level rise just as you can do sound. You can do your sea level rise and your sound afterwards as a self-consistent correction to the whole thing. But the exact way the fluid moves around, the eddies and the transport and the jets and all of those things are well enough described within the Boussinesq framework. So there's a nice separation of those sort of levels of the problem. And I say that because part of the controversy has consisted of people saying, oh, you could never use the Boussinesq for this because, look, it doesn't conserve mass, you see. You can't possibly let the sea level rise in a Boussinesq framework. Well, that's true in a narrow sense, but not true in the sense of computing the next correction. So there's no problem. Okay? Now, the energetics, just for the record, you can formulate using the idea of dynamic enthalpy, which I think was originated by Bill Young, but if someone else had it before, please tell me. But it's a beautiful way to handle the energetics problem. Essentially, you take the enthalpy, but then you put the pressure argument equal to the hydrostatic Boussinesq, infinitely big. You know, you're taking the Boussinesq limit, you're letting gravity tend to infinity, and delta rho over rho tend to 0, but you keep the pressure in the formula for enthalpy, but it just becomes the pressure altitude. And then you have a consistent energetic framework. And by the way, this is actually a key to proving the generalized theorem. If you look at the original Paparel and Young paper, you just have a trick of integrating vertically twice. Well, integrating vertically twice, that's to say an indefinite integral followed by a definite integral, that's equivalent to multiplying by z, you see. But that trick of multiplying by z gets awfully complicated when you bring in your nonlinear equation of state. So actually, but if you do it all in terms of this quantity, bingo, it suddenly becomes simple and clear again. So that's very, very nice. So that's an important idea, which I'd like to learn more about the origins of if it wasn't invented by Bill Young. Please let us know. Now, the rest of my talk, back to Lighthill and non-Lighthill. Why do we care about both sides of the balance-imbalance column? Because its answer is fundamental to everything, because understanding all the fluid dynamics, practically all the fluid dynamics, as several people have mentioned, require you to understand balance and PV inversion. For example, Rossby wave propagation is something you can't understand without PV inversion, and jet self-sharpening is something you can't really understand, even though there have been huge numbers of papers on jet self-sharpening that make it sound terribly complicated. But actually, most cases boil down to this idea that PV gets mixed on the flanks of the jet, which Peter already mentioned in his beautiful talk, which talked about 100 times more things than I can possibly find room for in this talk. I love this quote from Vladimir Arnold, who in his book on Hamiltonian mechanics says, Hamiltonian mechanics cannot be understood without differential forms. He says, well, I would say these things can't be understood without balance and PV inversion. I still marvel that the things aren't emphasized in textbooks. I'm going to skip over, this is an old thing of mine where I just show the jet self-sharpening thing that I discovered everybody had forgotten about when I went to the meeting in Savannah. Here I want to pause on this though, because this is another relation that's terribly well known but sometimes forgotten. It tells you that the eddy flux of potential vorticity, this is by the way in a zonally averaged framework, and as Peter pointed out to me the other day, we really have to think more about the non-zonal case, following jets around as they meander, but this is kind of what you get. It's not so well known that this was discovered by G.I. Taylor in 1915 for the barotropic case, the barotropic non-divergent case, and then generalized by Francis Bretherton. It's perfectly clearly put out in one of his 1966 papers to the three-dimensional quasi-geostrophic case. This is quasi-geostrophic. It's not the most general kind of balance, but it's so elegant and simple and basic that it's worth emphasis. I think we should call it the Taylor-Bretherton identity, or Taylor identity for short, and not just sort of put it in as a footnote that you hardly notice. Here's the three-dimensional version, which involves the divergence of this thing that we've traditionally called the Elias and Palm flux, but it might be better to be called the effective momentum flux, consisting of the horizontal Reynolds stress and the vertical form stress. That's the favorite way for ocean, and I think more logical way to talk about it. So it relates PV fluxes, including, this is nonlinear by the way, this is an exact consequence of the quasi-geostrophic equation. It's just a mathematical identity. It follows as night follows day from geostrophic balance and PV invertibility. So once you have that, you've got this eddy flux of potential vorticity, which could be nonlinear. It could be due to PV mixing on the flanks of a jet, or a stratospheric surf zone, or making a PV staircase on Jupiter, and it's related to this effective momentum flux divergence, which is often due to Rossby waves arriving from somewhere else. It's a radiation stress in the language of physics due to Rossby wave propagation. And there are other things about this. I'm going to skip over some of these things. There's a Phillips effect, which was mentioned actually by Richard Scott, if I remember. Wasn't it, Richard? Where if you've weakened your PV gradient, it makes it easier to mix, so there's positive feedback. And we discussed that in David Ritchell and I discussed that in our JETS paper. One thing relating to Richard's talk is that if you do these thought experiments in which you start with a monotonic PV gradient and then mix a sort of surf zone or staircase step out of it, there's a general result that says that when you do that sort of thing, you must get a negative angular momentum change. And in fact, my student Richard Wood has proved that for a general monotonic background PV, initial PV profile. It's another thing that everybody thinks is obvious, including me, until I tried to prove it, and it turned out to be quite tricky. If anyone else has done this, please let me know, because I think this is actually an original work result from Richard. I tried to prove it generally and failed, and he found a very ingenious proof by bringing in optimization theory, and then we found a simpler one. These cases are forming Jupiter-like staircases, and we've all seen this quite a lot. They all have negative angular momentum change, and the fact that it's a general property you can prove in this sort of way by taking a general mixing Green's function or mixing kernel. Gavin Esler's been using this a little bit in his work as well. And if you take that definition of generalized mixing, which includes advection, it's the most general way to have something that's mixing in which you cannot expand the range of PV values. Okay, that's the basic thing. And if you have uniform PV, it stays uniform and so on, and that gives rise to, and conservation give rise to these two constraints. So mathematically, it's a little bit abstract, but you can take this and prove that you always get a negative angular momentum change. And that's a work in, how many? Two. Right, so I'm going to skip some of these things dedicated to Rupert because, and all the Lighthill stuff, the classic Lighthill paper. Sugimoto mentioned, he's covered that already. That's the original Lighthill form of the sound radiation from unstratified, non-rotating vortex. The consequence that the slow manifold isn't a manifold. I hate self-contradictory. I don't like the solar constant being variable. I don't like geostrophic adjustment being ageostrophic. I don't like securitized investments being insecure. Human language is full of self-contradictory terminology, and the slow manifold is another one. It's not a manifold. It's not a nice smooth surface in phase space. It's a fuzzy thing. It's a stochastic layer, and Sugimoto already reminded us of that, so I don't need to emphasize any of that. I just want to remind you, though, of these amazing simulations by Warwick Norton that we published in 2000, in which one of these is a primitive equation evolution for 10 days on the right, and the other is a balance model using a very high order balance relation. And for a chaotic vortex merging and all sorts of stuff going on, and it still follows that closely in a balanced model. This is shallow water, by the way, is quite astonishing. Now, the rest of my talk, I'm going to have to summarize very briefly. The point is that in those regimes, they're astonishing because they're at order unity Rossby and Froude numbers. There's no right to be accurately balanced. But the reason they are seems to be to do with the fluviality of thin jets. And the point is that if you take the simplest model of this, the shallow water thin jet with a PV jump here, you always get phase speed within the range of jet speeds, and that means that you always get mixing on the flanks of the jet. Now, if it goes over topography, that goes out the window, and I think that's relevant to some of these ACC things. But the consequence of that is that the slow meanders of these thin jets have zero group velocity at first approximation. It's from Gavin Esler's work, and you see the sort of Gulf Stream-like behavior, and one big meander hardly knows anything about the upstream and downstream meander, so it's a zero group velocity thing, and the jet is a kind of flaccid river-like flow through stagnant surroundings to first approximation. And this movie that Peter showed and has kindly given me a copy of, which if it runs, if it doesn't run, you're going to have to remember what it was like, because it is, it's not on my screen. You see here's the Kurashia and here's the Gulf Stream sitting there. There's a river flowing through a kind of stationary surrounding. This is what I call fluviality and thin jet flaccidity. And that's one reason why those things of Warwick Norton's, though, are why balance works so much better than it possibly can. Now, here's the state of the art and high order balance. I don't have any time except to say that you've got inertial effects, including Bernoulli terms. These are the hyperbalance equations that exactly conserve mass as well. Now, the punchline of this talk is the O'Sullivan and Dunkerton type of emission is not a Lighthill process. It's almost the opposite in practically every way. And my JAS preprint, you can get off my web page, will give you the full details. But this is my last slide, Mike. This is what I do. I review the new work of Snyder and Viewdeth. It's very useful to review Viewdeth because Viewdeth is a very talented, ingenious, smart guy who does very interesting things, and he writes it all in his own private language. So you have to it's like translating Rosetta Stone. But so in my review, you will read an intelligible version of what he's done, including filling in lots of numbers he left out, which he kindly provided by email. But the point is, here's a plan view of a vortex dipole with a Bretherton PV delta function. This is the bottom half of Untitled dipole, which has anything but a delta function. It has a smooth pair of PV anomalies. It's three-dimensional stratified flow, and you get gravity waves coming off. It's a steady mountain wave-like process, and the wavelength shrinks to zero because of the wave capture process, and that's exactly why you saw those streaks in Peter Bartello's vertical velocity field. They're captured gravity waves. Wave capture means it's the horizontal critical layer effect, if you will. First discovered by Walter Jones, studied by Victor Schreier and Badulin, wasn't it? Badulin and Schreier, and Oliver Buehler and I have reviewed it, so we understand it very well. And that's what's going on here. You have these gravity waves having their scale shrunk exponentially fast, so it's no wonder they hit the grid scale in all the numerics. That's what you have in O'Sullivan and Dunkerton as well. It's now perfectly clear. I'll stop there.
Unfair to sneak my question first. In the first part of your talk, you were using the form of Znesco approximation. As far as I know, all these require you to assume a reference state for temperature and salinity and so on. Does that assumption get in the way of the
No. I mean, we've done it for the Wallis level of approximation, if you will. It's linear in salinity, it's quadratic in temperature, it has a PT, a thermobaric term, but everything else is linear. But that's the main nonlinearities taken account of. And by the way, it's the thermobaric effect that where the dynamic enthalpy pays off. That's what the thermobaric effect is awfully complicated unless you use the dynamic enthalpy.
So even though you're looking at something global scale, it's sufficiently accurate to assume a globally uniform reference state.
Oh, no, we don't need... No. It's not a reference state in the ocean. No, it's not that. It's a reference state in the equation state. It's just saying that salinity hangs around 30-something parts per thousand or whatever it is. It's that sort of reference state. It's a thermodynamic one.
What?
Is frontogenesis a captured gravity wave?
Oh, I should have mentioned Snyder's work on frontogenesis emitting gravity waves, because it has something in common with this. I like these examples, though, because these are truly steady, you see. They're much simpler. You can get hold of what's going on. The wave source is exactly here, and so on and so forth. And it's not Lighthill. You can't compute the vortex first and afterwards compute the waves, which is an essential part of Lighthill.
May I repeat the question, hoping you'll answer
Sure.
it a second time? Is frontogenesis a captured gravity wave?
I would say probably not, because I think of the Hoskins-Bretherton theory and all that. Well, that just says it collapses. It's a blow-up to finite time. It doesn't contain the gravity wave, does it? Because it's semi-geostrophic. So, let's see, have I understood your question? The whole thing can't be a captured gravity wave, no. Actually, Snyder's work says it doesn't capture in that case. They just come off and go somewhere else. Okay.
Frontogenesis can emit gravity waves.
Yeah, I
Out
think...
of the sharp W's that, for example, Peter was showing, are more frontogenetic than they are gravity.
Well, that part of the semi-geostrophic overgrowth.
Actually, Jim, I mean, your remark has a certain profundity, because the wave capture process is a consequence of the waves feeling a horizontal deformation field. So it's okay, it's the wave version of frontogenesis, if you will, but it's not the whole frontogenesis.